Okay, so here's the weird part now. We're going to start what's called a hypothesis test. So right now we're in the middle of probability. We just learned how to predict how large, we were able to predict or make inferences based on a sample that we have. You can also do this with confidence intervals. We can estimate a population parameter after we found a confidence interval, but another way to make a statistical inference is to make a decision about that parameter. This is called hypothesis testing. So rather than using a point or an interval to estimate a random sample to approximate the population, we're going to test the correlation coefficient, or we're going to test a hypothesis and use that to decide whether or not these have a significant correlation, linear correlation. So, sorry, just a second. Okay, so before you can test a hypothesis, you need to first collect a sample, okay? Then your data needs to follow some criteria. It needs to be quantitative, so numerical data. It needs to be from a random sample. The scatter plot, after you create it, needs to roughly show that there's a linear trend, whether it's positive or negative. There are no outliers, so no people fall within 3 significant, we didn't find that. So no people fall way outside the data points. The variables x and y are both normally distributed. If those 5 criteria are met, then we can run a test to decide whether or not these two data are correlated. To do this, we use a hypothesis test. You can have a null hypothesis and an alternate hypothesis in your hypothesis test. The null hypothesis is the status quo. What you assume is what you're looking for. So in this case, we have no correlation. That's what we're going to assume. We know nothing about how they're correlated. And then our alternative hypothesis, in this case H sub 1, is rho does not equal 0. So we're just testing, is there a correlation? There either is 0 correlation or there is not 0, which means there is some correlation. And then we'll say afterwards whether it's positive or negative based on the correlation coefficient. So in our case, you're always, for this chapter, we are going to have either rho equals 0 or rho does not equal 0. That is our null and our alternative hypothesis. And that's this little letter right here. It's a Greek letter R. It looks like a little P. We're going to do a full hypothesis test. You can run this a little bit differently by just checking the p-value with the test data, and I can show you that in a second. One thing I did forget to mention is that this correlation coefficient that we are finding is a specific type of correlation coefficient. This is called the Pearson correlation coefficient. For this hypothesis test, because we've assumed that both variables are normally distributed, we can run a t-test. A t-test distribution looks very similar to a normal distributed data, but the height of the distribution changes based on the number of sample sizes. So we'll do a t-test with what's called n-2 degrees of freedom. So that is the height, and that's just, again, based on the number of data points. So the t-test has a test statistic used with a variable t, which is equal to the correlation coefficient r times the square root of the degrees of freedom divided by 1 minus the square root of the correlation. Okay, here's our first example. The correlation coefficient for the height of a building, R, was 0.927. let's test the significance of this value at alpha equals 0.05. So that alpha is the area underneath the curve of the distribution that we're looking for. We want to know how many people fall, or what's the proportion of people that fall within this data point. If we can find a lot of information in that data point, then it's not an outlier area, if that makes any sense, if you think about what we were talking about in our last section. So here is the curve of the distribution right here. We know that the correlation coefficient is strong positive. So we know that we've done the scatter plot and it's linear. We know that both are normally distributed. So all of our criteria work out for this. Our data is quantitative, it's numbers. Our sample was random and we didn't have any outliers. So we can run this information. Okay, so you don't have to run this correlation coefficient by hand, by the way. I know that we did. But when you're doing these problems for your homework, you just highlight the table, insert your scatter plot, check that it's linear, and then you can add this regression line or the correlation coefficient onto it by putting the plus sign, adding the trend line. Once you have the trend line, double-click the trend line. I'm sure there's a better way to do this, but this is how I remember. And we're going to display the equation on the chart, and we're going to display the r squared on the chart. The r squared is the square of our correlation coefficient. So if I find the square root of 0.86, should give me my correlation coefficient. So I went the long way when I showed it in the example, but you can get that information off of the scatter plot. So same number right here. I'm not going to be looking for the information the long way unless the problems in the homework ask you to specifically do it like this. You can go ahead and use it from your scatter plot. Okay, so from that information, we can say it's got a strong linear correlation, but we want to test for sure. Okay, so to run a hypothesis test, you first write your hypothesis. Our hypothesis is that our null hypothesis is no correlation, but we are testing the alternative hypothesis that there is a correlation. So that is our H1. Then from there, we need to run our test statistic. So I've done that over here, and we need to find our critical value. So we find the critical value from either the TI Inspire or the 84 or from the charts. I believe in your homework problems, the charts are connected to the problems that you need. I have a snip of the chart right here. What we want to do is mark off the significance level on our t-distribution. So here's our bell curve. If we have a 0.5 alpha level, and we have an equals and not equals, that tells us a couple of things. The equals and not equals tells me that I have a two-tailed test. So I want to know how much of the data is at the end of the bell curve and at the beginning of the bell curve. And I want to know how much data is in 0.025% of that area. So that's what's marked off on this curve. This shaded in yellow area is my significance level. Then I've taken that number and my degrees of freedom, and I go over to the chart here. And on the chart, we have degrees of freedom is the number of items you have minus 2. So in this case, 6 minus 2 is 4. So we're going to look under degrees of freedom 4. We have a two-tailed test. So, and the amount in our tails is 5%, which means the middle that we're also looking at is 95%. So we're going to go over here to the column that has a 95%. Our tail is set up, our z-score is 2.776. So that is what this number is, 2.776. That's called the test significance level. If our data falls between the test significance level, we do not reject your null hypothesis. But if it's in the outsides of our tails, then we are going to reject the null hypothesis. So now we need to run our test statistics. That's our T with this formula right here. We're going to plug in our R of 9.927. Degrees of freedom is 4. That's in the top. And then here's the 0.87 right here, giving us a test statistic of 4.943. Okay, if we put that on our bell curve, the 4.943, that lies right here. That's inside the shaded region of our significance, of our alpha level, significance level. So because of that, we can make a decision. So we made a decision rule by setting up a rejection region. That's the shaded area. If our number fell within the non-shaded region, in this 95% of the bell curve, we would accept that there's no correlation. But in this case, our t-statistic fell in the shaded region, so we have to reject the null hypothesis, and we can say that there is a correlation. Because the correlation coefficient is so high, we can say there's a significant correlation between these. Significant positive linear positive correlation between the height of a building and the number of stories that there are. Okay, the last thing in this video is correlation versus causation. Just because these two things are correlated does not mean that one causes the other to happen. So there is a big difference in finding the relationship between a variable and saying that because this variable happened, this other thing is always going to happen. So it rained outside, then we can say that the ground is wet, right? So because the ground is wet, it probably rained outside. Does that happen every time? No, but so it doesn't go backwards, but it does, you can say that this causes the other. A correlation can just mean that something happened. So for example, there are more car accidents outside because it's raining. We can find a relationship between the weather and car accidents, but we cannot say that 100% of car accidents are caused because it's raining. And here's another example. Ice cream sales and weather and sunburns. So you can have the heat can cause ice cream sales to go up, or it can cause a sunburn. But then we can find a relationship between the number of ice cream sales and sunburns. Okay, now I kind of mentioned this. We can find a regression line that falls between both of our data points, and I showed you how to find that in Excel, but it is a linear equation. Oops, sorry. So in this example, this is the regression line. It's the line of the equation of the line of best fit. It's the equation of the line of best fit. Y equals a plus bx, or y equals mx plus b, where b is the slope and the a is the y-intercept. I'm going to come back and talk to you about residuals and what they mean. So check me out in the next video for the next section.